Okay, so I'll do my best. Some days I'll forget, but I will try to record the lesson. Okay? So, because some of you, your mic not here, right? Then you can rewatch it. Yeah? Okay. So I expect to see by now your OneNote set up, and you should have your CA 1.18 on standby. Yeah? Good. Okay, your homework for yesterday was to get you to play around with this particular simulation over here. Okay, you have seen that you were asked to do several things. Do you have the simulation on with you now? Okay. If you have not, could you just put the simulation up? So I'm going to do a quick review. Okay. Could you take partial charges? You can take partial charges. Then do you see the partial charges? A symbol that looks like this. Do you see that? Yeah? Okay? What are we covering today? Today we are covering polarity. Polarity of covalent bond. Then the next thing we'll do is hydrogen bonding. Okay? I'd like you to draw your attention to these two symbols over here. Okay? Do you recall in JH2 you learned about ions? See the knot here already. You all learn about ions? Yeah. Okay. So you learned that ions, there are positively charged ions, there are negatively charged ions, yeah? Right? Okay. This symbol over here that you see, this delta positive, this delta negative symbol, this does not mean that it has become an ion. It just means that it is slightly charged. Okay? It just means that it is partially charged. Okay, could you write this down somewhere in your OneNote or into your CA? Okay, when you see this symbol, it means that it's partially charged, either partially positive or partially negative. Ions are fully charged. This one? Oh, I said delta. It's just the name of that symbol. Okay, thanks for the question. Yeah, so just stop me anytime to ask questions if you have. Yeah. Okay, partially charged. I'm going to do a little demonstration. Yeah. What is that symbol, is it?
Yeah,
What is this symbol? Yeah, it's just like, it's called delta symbol.
Oh.
Yeah. It's kind of like a D with a swoosh on top. Okay? All okay? Right. Now I'm going to do a quick recap. Okay, let's talk about functional groups first. Let's do a recap from yesterday. Okay, I want to see how much you remember about functional groups. Here's a very quick one. I want everyone to look at this molecule over here. How many functional groups do you see? Please discuss with your friends right now. I'm going to invite someone to share with me. Okay? How many functional groups do you see? Remember, the skill is to be able to spot patterns. Do you see any functional groups? Ready? Okay. Some of you noticed that it's the same molecule that you encountered before. Yeah? Okay, Kyra. Kyra? Oh, Kyra is here. No, I thought Kyra is there. Kyra. Okay. Do you see any functional group? The phosphate group. Okay. Iliana? Okay, Iliana. Do you spot any functional groups? Okay, the same group. Okay, because Iliana is closer, right? Iliana, do you mind just like helping me to direct where the phosphate group is? Okay, just show the class. Where's the phosphate group? Yeah, okay, circle for me. Where's the phosphate group? Okay, thank you, Iliana, and as well as Kyra. Okay, so can you spot patterns? That was the lesson from yesterday. Okay, because moving forward, we need you to have these eyes. We will spot these patterns fast. Yeah. Today we are going to move on to the next part of our lesson. Yesterday we learned about functional groups. Functional groups are all about the way in which atoms bond with each other. Okay? And we realized that the way atoms bond to each other, there's a pattern. What bonds hold these functional groups together? Okay, that's the next question. What kind of bond holds these atoms together in place? You've only learned two kinds of bonds so far, right? You've learned ionic as well as covalent. Okay, so my question to you is, what kind of bond is holding all these atoms together in our body? I hear covalent. Covalent. Okay, so here's the next thing. Covalent bonds. The atoms in all the biomolecules, a lot of things in our body held together by covalent bonds. A lot of it. I wouldn't say all, but a lot of it. Today's lesson is all about covalent bonds. We want to understand covalent bonds a little bit better, because what you learned in JH2 was just the surface, the tip of the iceberg. Today we're going to learn about how some covalent bonds are not quite equal than others. Some are a little bit more special than others. For us to understand that, here I have a small little demo. What makes a covalent bond a covalent bond? Sharing of electrons, right? Okay. So here I have two hydrogen atoms. They are sharing the electrons. Yeah? Here I have two electrons being shared. Okay? And they kind of share it equally. Okay? They share it equally. This is a covalent bond. I want you to observe what happens if I have to say oxygen. Let's say I have oxygen bonded to hydrogen. Okay. Again, do you spot the pattern? What functional group is this? Quickly, come discuss with your friends. What functional group is this? Okay. Hydroxyl or seal. Okay, hydroxyl or seal. Okay, must spot these fast, the functional groups. However, something interesting here. Wrong demo. Here's the correct demo. Even though this is a covalent bond, they don't quite share electrons very equally. Okay? They don't really share the electrons equally. What do you observe? Say again, Alpha. The electrons are more on the oxygen side. Right? The reality is this. Not all covalent bonds, electrons are shared equally. In most cases, in a lot of cases, the electrons are shared unequally because one of the atoms may have a tendency of pulling the electrons more towards itself. Okay? We refer to this as electronegativity. Anyone saw the word while playing the activity? Okay? The word is electronegativity. The higher the electronegativity, the more the atom wants to draw electrons to itself. So if we look at this fellow over here, which atom has the higher electronegativity? Sorry? oxygen has a higher electronegativity. Yeah? The simulation that you played with yesterday was a digital version of what I'm showing here. Okay, for those that didn't quite understand the simulation, imagine now if I put the partial charges here, electron density. Okay? Electron density refers to how much electrons are being drawn to each side. So the more dense it is, means more of the electrons are towards the side of this particular atom. Yeah? So, if I have both atoms having the same electronegativity, both in the middle, you'll find that the electrons are shared quite equally. But what if I change things up a bit? What if B has a very high electronegativity? Notice that the electrons now are denser around B when B has a higher electronegativity. Let's flip things around. What if B is the one that is normal, but A is the one with high electronegativity? Now the electrons are drawn towards A's side. Yeah? I want you to make a prediction. Now both of them are equal. If I put B with more and A with less, what do you predict the electron density to look like? Yeah, say again. If B I shift to the more, A I shift to the left, what do you predict the electron density to look like? Where will electrons be drawn to? Okay? Who says A? Who says B? So we see, so I get a feel that you're understanding this. Okay, more, less. But notice that, you see, this symbol is getting bigger. Yeah? It is, the charge is getting bigger. Every time you see that something is partially charged, we refer to this covalent bond as being a polar covalent bond. Okay? So, we've just learned that actually covalent bonds, there are two kinds. There are covalent bonds that are non-polar. We have non-polar covalent bonds, and we have polar covalent bonds. I'd like everyone to have a quick discussion. Under what scenario for A and B will you find non-polar covalent bonds? Okay, this toggle over here, under what scenarios will you find non-polar covalent bonds? Okay, this is one scenario where you will find non-polar covalent bonds. Both A and B, the electronegativity is in the middle. I would like to invite someone up to demonstrate how you can create a non-polar covalent bond by shifting, even after shifting the toggle. Possible? Can you create a non-polar bond by shifting the toggle? Ready? Ready or not? You discuss with your friends yet? I'm going to start calling names. I want to get to know you better. Well, not everyone here takes bio. Yongshe? Oh, doesn't take bio. That's what lucky. Daniel? Doesn't take bio. Wensin? Yeah, okay. Wensin ready? Okay, if I invite you up, Wensin will now toggle A and B, the electronegativity, but she will create another non-polar covalent bond. Okay, go ahead. Oh, my mouse pen not working. Okay, what is Francie doing? She shift A to less, shift B to less. Is it a non-polar covalent bond? Yeah. Give a round of applause for Francie. Is there one more scenario you can do to create non-polar covalent bond? And that scenario would be more, right? More and more. But truly, is there only 1, 2, 3 scenarios? Actually, it's infinite, right? If I wanted to, it can be slightly over here and slightly over here. It is also non-polar. So what is the key idea here? A covalent bond is non-polar only if there is no difference in electronegativity. William, can you write that down? Okay, that's the key idea here. If there is a difference in electronegativity, you will find that the covalent bond starts to become polar. Spell continue. Continue. Oh, one more U. Oh, there are 2 U's. Continue. Right now. Yes, hi.
What is A and B?
Oh, A and B are just random atoms. Okay, just random atoms. Okay. So, I would like to draw attention to the screen again. We agree that if electronegativity there's no difference, it will be non-polar. Now I'm going to toggle A. Watch what happens when I toggle A towards the less. Okay, watch what happens. Oh, it starts to grow bigger and bigger, right? Okay. So, the larger the difference in electronegativity, the more polar the covalent bond gets. Make sense? Yeah? So that's the next key idea. The larger the difference in electronegativity, the more polar the covalent bond is. And if I max out A to become the extreme less, this covalent bond is extremely polar. Yes, Hoya?
Why would electrons go towards the place with more negative?
Great question. So then, you'll be wondering, right, gee, what makes an atom electronegative? Why would an atom want to attract electrons to itself? Okay. This will take quite a deep dive into chemistry, but if I put it very simply, it has to do with the increasing number of protons. Protons are positively charged, yeah? So the more protons an atom has, the more it wants to attract electrons. Okay? So you would find that when you look across the periodic table, the more protons there are, typically, the more it attracts electrons. Okay, so that's how I have a question. So that takes you one level deeper. Now, if you are ready, we will look down at the examples. They ask you to draw the electron density and partial charges on the following functional groups. This is what is expected of you. I'm going to demo one for you, okay? We've just looked at oxygen and hydrogen. What group is this again? You keep practicing, hydroxyl. This is the hydroxyl functional group. Okay, when they ask for electron density, what they mean is that we just want you to draw a rough cloud. Okay, a cloud of electrons. What do I mean by that? Just now when we play with the oxygen and hydrogen, we find that most of the electrons kind of get attracted towards oxygen, right? But imagine now if it's very, very strong, then you have to keep drawing this diagram bigger and bigger and bigger. It doesn't look very nice, right? So instead, we can represent it in another way. We can draw the electrons to look like a cloud that's surrounding them. Okay? Yeah? This kind of shows that the electrons are being pulled more towards oxygen. Okay, this is what electron density means. Yeah? If it is kind of attracted to each other in an equal way, it looks something like this. Hydrogen, hydrogen, then it looks something like that. Okay, like same. But this one is more towards this side. Next, they ask for partial charges. Okay, I want you to think, this one you think for yourself. If an atom attracts electrons towards itself, will it be partially negative or partially positive? Okay, can everyone have a think? Discuss with your partner. If all the electrons are drawn towards this atom, will it become partially negatively charged or partially positively charged? I hope there's some logic to this. Okay? Sorry, so this three, yeah? Not here. Ravindra? Kiran. Oh, sorry. Oh, okay, now I see. Okay, Kiran. So, Kiran, will oxygen be partially negative or partially positive?
Partially negative.
Why?
Because when ions gain an electron, it's not negatively as well. It's not negative. So if the electrons go this way more, it should be partially negative as well.
Okay, yeah. Kiran brought back the example from last year. No ions, when there are two atoms, if one gains electron, it becomes negatively charged, the other one becomes positive. So think of it the same way. If it's a covalent bond and the electrons kind of gather in this region over here, you'll find that oxygen will be partially negative, hydrogen will be partially positive. Henry? Partially means just like, okay, this is partial. Fully would mean that they are not connected by a bond. Separate individuals, they have a charge of their own. Okay, this is partially charged. Okay?
Everything which is one is partial.
Yeah. Okay. So if it's a covalent bond, we say that it's partially charged on either end of the atom of the bond. So this particular covalent bond is polar, and it has a partially negative side and it has a partially positive side. Okay? But just now I just told you up front that oxygen is more electronegative, right? But is there a way to find out who is more electronegative? There is a way. If you Google online periodic table, electronegativity, this is what you will find. You will find a table with all the electronegativity inside. Look at oxygen over here. Electronegative 3.44. Let's look at hydrogen, 2.20. Okay? So the more red it is, the more electronegative it is. So this is how I found out. I would like you now to try on your own. There are remaining bonds below. Can you find one of these periodic table, type periodic table electronegativity, drag and drop it into your notes, try the remaining questions. Okay? The next one I believe down below is carbon and hydrogen, right? Okay, so what I do is this. I will write down the electronegativity first. So based on the periodic table, oxygen is 3.44. Hydrogen is 2.20. Okay, so this one is more electronegative, so the cloud will look something like that. And then this will be negative, this will be positive. I'd like you to try it for the remaining bonds, remaining covalent bonds. So the next one is carbon and hydrogen. What would that look like? Okay, can everyone try the remaining ones? And then I'll go around to support you if you need help. Just raise your hand. Okay? Oh, okay. So like, how different must it be? Yeah, correct. So actually this is very little. So actually we don't consider this. But then you notice this one now. Right? This one is actually, this was like a, how much? 0.38. So I read online, SH also considered non-polar, some considered slightly polar. If you say non-polar, you say slightly polar. Okay? But for carbon and hydrogen, we usually say that it's non-polar. Okay, I'll give you until 9:30. Okay, I'll give you until 9:30 to try it out. And then we'll invite some friends to come up to draw the various answers. CH. NHSHC double one O. All of them seems to be true. You made it look like all of them are the same. Are they the same in terms of do you look at the periodic table? Yeah, this one of it. You see, oxygen is 3.44 compared to carbon. So you draw your electron density, right? Now we look at carbon. 2.55, 2.20. Should the density be exactly the same? Yeah, so draw it relatively. So if this one you draw it like that, the partner one, the electron density is slightly smaller, right? Yeah, it needs to be proportional. Yeah. But it's like one factor, yes. So there are two factors. The number of electron shell and the number of protons. The more electron shell you have, the weaker the electron. Okay, so can I get you to draw the electron density proportional? Because currently everything is the same. All school is the same. Okay. Yeah. Can I get? You know why like that?
Yeah.
So your answer, that would be allowed. Oh, I understand. Okay. What I mean to say was that what? Yes. So what we look at is how big the difference is. Not say what the difference is, but you take the large one minus the small one, you get the difference. Oh, the greater the difference, greater. Thank you. Hey, can I invite some you up? Pardon me, I'm still trying my best to remember your names. Huh? Young lady. Jeanette. Jeanette. Okay, what? You go. Anything? Choose one. Jeanette. Yeah. Phinia. Phinia. You choose one on the top. Oh, Jeanette. Jeanette. Always see you around. Can't remember. Eachen. Why do I always see you? This also. Always see you. I always know that you're running. Okay, thank you. Jeanette. Philia. Right. So here we have Jeanette's work. Here we have Phinia's work. Okay, I'm going to get two more. SH and C double bond O. What? You want this one? Is this supposed to be somewhat equal or what? You want to add comment? Okay, Jeanette. Yeah. Go ahead. Choose one to do.
Are we like in the I realized it's picking out everything.
Which one will work for you?
Put it like back a bit. So the point is not yeah, I think I like this. The point is up here.
Last one, C double bond O. Okay, C double bond O.
Not
C. I'll try to understand what's happening. Yeah? Oops, what is this supposed to be? Oh, okay, thank you. Yeah, yeah.
Is it okay if I draw like one gigantic circle, then I will just
Yeah, you could. Yeah. Thank you, Susie. Okay. What is this? Is 3.1? 4. Okay. Alright, let's have a look at the electron density and partial charges. First and foremost, let's look at the partial charges here. Carbon, negative, positive. Negative, positive. This one? Actually, that will hit. Negative, positive. Okay, negative, positive. This one? Positive, negative. All got it? Okay, next level. Let's look at the electron density. Okay. Here, we see that 2.55, 2.20. Okay, what is the difference over here? It's around 0. In my mind, right there, 35. Okay, 0.35. So the difference is, what is it? Come on. Okay, the difference is very big. This one, the difference is very small. Okay, how small? It was 0.38. Okay, this one is 0.89. Okay, this one is pretty big. Okay, now just now, my God, my brain. Wenxin Wenxin? No, Wenxin is here. Behind Wenxin is Iran. Inside Iran is? Kyra. Okay, just now I called Kyra here, but Kyra is here. Okay, Kyra said that, Kyra did a little bit of research because she had this question in mind. How large must the difference be to be considered polar? Okay, actually, among scientists, we have agreed that to consider something polar, the difference must be more than 0.4. Okay, so we just put across the board now. Which covalent bonds actually won't be considered polar? This one, as well as SH, right? So SH and this one, and carbon hydrogen, we typically consider them non-polar. Okay, non-polar. However, you will find in some sources that because this is 0.38, very close to 0.4, sometimes some sources say this is partially, slightly polar. Because it's so close to 0.4, some sources you'll see them say slightly polar. Yeah? So what will the electron density look like? Yeah, it will look almost, it will look like carbon is pulling a little bit, but actually they'll look quite similar on both sides. Okay? But because it's less than 0.4, actually we don't normally put down the partial charges if it's less than 0.4 difference. Okay? Still follow? Yeah, so when something is non-polar, less than 0.4, we usually don't put down the partial charges. We consider it non-polar. Let's look at nitrogen and hydrogen. The difference here is pretty big. Big, whatever big is. So you would find the electron density to be skewed more towards nitrogen. This is okay. This is a polar covalent bond. It is a non-polar covalent bond. This is a non-polar covalent bond. This one over here, the difference is quite big. Nicely drawn, that is skewed towards oxygen. This is a non-polar polar. Oh, this one, CO. Polar. Okay. This is a polar covalent bond. Okay. So far in our journey for biology, we've learned two things. Number one, we've learned about the patterns in which atoms can bond with each other. And we learned that the bond is typically a covalent bond. And right up to this point, we've learned that not all covalent bonds are equal. They can be polar in nature if there's a difference in electronegativity. Okay? I'll take a short pause here for you to organize your notes, to draw whatever you want to draw, and I'll go around taking questions. After this, you're going to have an activity. Okay? Yes, boss. Don't need. It's just so that you help you understand this stuff. Don't join. Yeah. Oh, if it's not polar, right? We usually just draw both sides, look quite similar. Okay, if it's any comfort to you, I will never ever ask you to draw this during your exams. Okay? Why are we doing this? To help you visualize polarity. Okay? This is just a beginner activity. Just help you visualize can already. Okay? Some of you are drawing beautiful notes. Yeah? Okay, so in a while I'm going to get we're going to do activity, so I'm going to need some help. This is my traveling box of wonders. Okay, often in this box I have a lot of activities prepared for you all. Okay, can I get some help? There's carrots. Don't take my Bible. Carrots. Okay, carrots. Carrots is in the corner. Okay, right now I'm going to go about distributing a dropper to each pad. Okay. Let's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Each pair should have a dropper. You have a dropper? Okay. Okay, we're going to play a little activity. Okay, we just done. Okay, we just completed one checkbox today. Okay, now, can you look around? Make sure you are either in a pair. If you want to work alone, it's possible for this activity. Okay, or you can work in threes if you want to. Hey, don't poke yourself. Okay, next thing up. Can you look into your wallet? Can you take out a 20-cent coin? Take out a 20-cent coin. Okay, next. Do you have a device that you can use to record things in slow motion? Okay, in your hands. Okay, can you take out a device that can record in slow motion? Okay, a very simple activity I would like you to do. Okay, we have moved on to the next class activity, which is CA 1.1B. Okay, will you stand by this in your notes first? Okay, stand by 1.1B. It's already in your Google Classroom, so transfer it into your notes. We are going to play the first activity. Okay, why ask you on 20 cents? Actually, you want 50 cents. 20 cents? Okay. Remember, 20 cents is okay, 20 cents is okay. Okay, we're going to do this very simple activity. It's quite fun. We will first place a 20-cent coin on a flat surface, must be flat. Next, we will record a video in slow motion as you add more droplets of water onto this 20-cent coin. Okay? I would like you to add it onto the surface of the water, meaning add drop by drop. Don't let the drop. How to say this? So, imagine this is your coin, and then the water starts to accumulate, right? When you add the drop of water, don't add it too close to the droplet itself. Leave some distance away so that you can take time to like plonk into the droplet. Yeah? Okay? Stop recording when the water overflows your coin. Okay? Then after that, I would like you to rewatch your slow motion video and see if anything happened. Okay? Okay, so this is what will happen now. I'll go around with this magical water. Each one of you take, don't take my own water bottle. Okay, my droppers, right, has been used to take out a lot of chemicals. Okay, so I'd like you to fill your dropper up to the brim and then stand by. When we say go, then you can begin activity. Okay, come. Okay, do you fill up? Okay, everyone stand by. Okay, take as much water as possible. Okay, you your dropper is fault, please let me know. Yeah, okay, quick. Suck. Okay, so stand by. One person can do the recording, another person stand by to. Can read. Oh, don't need. That's the max you can put. Okay, come. Okay, can. That's the max you can put. Okay, can I also get? Okay, let's make a competition. You can also count how many droplets you manage to add onto your coin. Okay, let's see how many droplets you can get onto your coin. Hey, but everyone must be 20 cents. If you suddenly use up 50 cents, then you will have more droplets, right? Okay, are you ready? Okay, you should be recording and you should also be counting. On your mark, get set, go. Go. Why so slow? Overflow already. If you're done recording, have a look at your slow motion video. Anything interesting happen? Don't worry, I'll let you do it one more time because once I let you see my video, you will want to try it again. Okay, is everyone done? Alright. How many drops do you manage to put on the water, on the coin? Yeah, I want to hear how high it goes. Say it. 22. Anyone went higher than 22? Okay, what's yours? 34. 36. Okay, you have a winner. Yourself?
We used 50 cents, so we got 49.
Yeah. Okay, 36. Anyone else beat 36? Okay, not bad, right? You managed to put quite a lot of water droplets onto the coin. Anyone was quite surprised by that? Yeah, when I first did it, I was like, wow, how come the coin can hold so much water? It's as though it didn't want to spill over. It was kind of holding itself together like that. Yeah? Okay, I'm going to show you my slow motion video. Okay, have a look. I don't know how many of you managed to see this. Did you see that? Boing. Oh. Anyone wants to try again? Okay, you want to try again? Okay, come, I'm going to go around. You can take more water for yourself to try. Okay, once you got your water, you can try again. you only light MV. I find that if you take from a side view, it looks better. Then you can see the image better. I find that if you give a little bit of room between the droplet and the big droplet, you can observe this phenomenon. Anything above 40 is cheated. Your each drop very small, right? Good. You know what's funny? How you can redo by sucking up the water on the table. Very resourceful. I thought I saw a droplet there. I thought I saw something bounce on the surface. Oh, so it's my fault. Okay, may I get everyone to pass the droplets back to the front without the water? I don't know where you want to spray. You can spray on your shirt, I don't care, but I want an empty droplet back. Okay, pass to the front, please.
Super slow.
Please don't add the water into each other's water bottle, yeah? Still got water or not? You sure? Okay, may I have your droplets? There's still water and spray on you. What is that still have? Huh? Can I get the droplets back? I feel like I just need a big droplet to fill up the water. Okay. Hey, why you not giving each other money? We just observed something quite magical, right? On the surface of the coin. Yeah? Aiyo, I packed already, then you okay. So we just observed something quite magical on the coin. But this is a science lesson. You want to understand how. Why is this able to happen? I'd like you to discuss in your pairs. What do you think is happening to allow for this to happen? Okay, speculate. Okay, speculate. They can write wrong answers. Hey, what are you doing there? Okay. Yeah, you can say survey session, but what does it mean? Okay? Okay? Alright, discuss, right? What do you think is happening here that allows for what we've observed? How is the water able to bounce on the top? Okay, the water got tension. What do you mean by that? The water droplet? Yes, it's coming down. Quick. Yeah? Yep. Okay, because there's a tension where? At the surface of the water, okay. So number one, there seems to be some sort of tension on the surface of the water. Okay, let's go a bit deeper. Why is there tension on the surface of the water? No more space. What do you mean by that?
Water here, then no more space.
Oh, okay. So perhaps it's an issue of space. Maybe the coin is already filled up with water. This additional water droplet comes out, not much space left. Any other speculation of how this is possible? Why is there this tension on the surface? Henry? Your wildest guess. Why is there this tension on the surface that prevents it from falling?
Water, when it comes into contact with the coin,
Yeah?
there's different density.
There's a difference in?
Density.
Oh, density.
Yeah, that's why your flow becomes.
Oh, okay. Henry says perhaps there's a difference in density. So you're saying maybe the small droplet has a lesser density, is it? Oh, okay. Perhaps it's an issue of density. Okay? Alright. So what we just learned in the previous segment of the lesson links to this. Okay? We notice that the water isn't quite able to penetrate immediately at least. We also find that we can add a lot of droplets of water and it doesn't quite spill over. It's as though the water molecules are holding each other together. Yeah? Okay, so actually that's a clue. Between the water molecules, there is between the water molecules, there is the bond. The water molecules are attracted to each other in some way. That creates some sort of a tension on the surface. But how? How are the water molecules creating this tension? A student gave me an insect, and I couldn't find a place to keep it, so I kept it among my stuff, and I got shocked when I opened it. So they gave me a cicada. You know what cicada is? Yeah, I found it somewhere in the school. Oh, I got shocked, man. So, I'm using all these magnets to represent water molecules. Okay? The red represents, what am I guess? What the red represents? Oxygen. Then the 2 whites represent hydrogen. So that means for each one of these over here, if I were to zoom in, it is O and H. Yeah, there's an O and an H. Okay? Imagine now, this is the surface of the coin. And I add all these water molecules onto the surface. Okay, they are coming out from the dropper. How will these water molecules attract each other on the surface of the water? This relates to the what we just learned over here. Okay, it relates to something we just learned over here. How will these water molecules attract each other on the surface of the water, of the coin? Okay, so now for next activity, I have little bags. Each bag contains the same things you see on the whiteboard. Okay, I'll like each row to take a bag, 2, 3, 4. And I've given you some water molecules in these bags. I'd like you to model how these water molecules interact with each other on the surface of the coin, on your table. Okay, in your bag you will find these tiny little versions of what I've got. Okay, I'll like you now to arrange these water molecules on your table to depict how they will interact with each other. There is a logic to how they interact with each other. It is not any old how good one. There is actually a logic to it. I'd like you to link back to the previous chapter on polarity. Okay, I'd like you to link back to this polarity. Here's a clue. How will they interact with each other on the surface of the coin? Link back to polarity. That is the clue I'd like to give you. Okay, once you've arranged, I'd like you to take a photo. Okay, both of you take a photo. This will be inserted into your CA 1.1b. Okay, once you're done arranging, I'd like you to take a photo. Okay, so this is the copy. Okay. Yeah, the clue is polarity. The clue is in polar bonds, polar covalent bonds. Here is the next clue. Okay, you don't know this, huh? Oxygen will be partially what? Okay, can you see that this is a polar bond? A polar bond? Yeah? Okay, so my question is, oxygen is partially positive or negative? Negative. Okay, oxygen is partially negative, so here is a negative. What about the hydrogen? It is partially positive. Okay, what if there's an attractive force going on here? How do the water molecules interact with each other? Given that every water molecule is partially negative at O, partially positive at the H, how would they interact with each other? Okay, please try now on the table and snap a photo. Given that all the hydrogens will be positively charged, partially positively charged, all the oxygens partially negative, how will they interact with each other? Once done, please snap a photo. Okay, once done, snap a photo. This will go into your CA 1.1b. Okay, so when you hand it up, I expect to see your test photo, not a selfie, of the water molecules inside the worksheet. What's the range? But that's up to you. So you decide the range like that? Randomly, Okay, now since you're playing with that, is there a logic to how they interact? Okay, yeah. Sorry? What? Oh, how do I have picture? Okay, how do I have picture? Good question. Hit insert. What's insert? Okay, then you press anywhere you want. Okay, then you insert picture. You need to click onto your worksheet. Then you click insert. Okay. Alright. I would like to now show you a simulation of how water molecules interact with each other. This simulation you can also find inside your CA 1.1b. I'm going to start the simulation now, yeah? I'd like you to have a look. How do they interact with each other? Let's go. It's kind of fast, right? But you observe how they interact with each other. Okay, I'm going to pause in a while. Okay, let's look at this. slow motion. What do you notice? Okay, they are bonding to each other and they are also unbonding. Great observation. This interaction between each other is kind of temporary. Right? It comes and goes, comes and goes, comes and goes. Okay. What else do you observe? How are they interacting with each other? Is there a pattern in which they interact with each other? Okay? An observation is that the hydrogen seems to be attracted to the oxygen. Do you see that? Look at all the hydrogens. Every time it comes across an oxygen, there's like some interaction when it's close enough. Right? Let's look at some other hydrogens here. When it's close enough to the oxygen, it starts to form an interaction. Can you see that? Yeah? So, what would the water molecules look like when they land on the surface of the water? Okay? Shameen, may I invite you to come out and rearrange these water molecules on the surface based on how they interact with each other. Okay, imagine we take a snapshot, a photo, frozen in time. How will these water molecules interact with each other on the surface of the coin? Imagine there's no water, they just landed. Oh, first one. Okay, first one landed. Okay. Look at how Shameen is going about doing this. She's doing it with some pattern. Right? It doesn't seem like she's just lumping everything together. There seems to be a logic she's applying to this. What is this logic Shameen is applying? Can you see what's happening? Okay, Shameen, could you share how you went about rearranging this? Okay, she put the hydrogen and oxygen together. Why? How young can hear Shameen?
Yeah.
What did Shameen say?
Positive charge.
What is a positive, partially positive charge?
The white color,
What's the white color one?
the hydrogen.
Oh, okay, the hydrogen. Okay, thank you, Shameen. Okay, round of applause, Shameen. There is an attraction, right, between the partially positive of the hydrogen and the partially negative of the oxygen. There is an attraction. We refer to this attraction as a hydrogen bond. Okay? We refer to this attraction as a hydrogen bond. You will see this bond appear across the various chapters. Okay? This is the first time you're seeing it. I'd like you to take note somewhere. Okay, hydrogen bond. Here's another way of seeing all this. Okay, this attractive force between a partially negative and a partially positive, or two polar covalent bonds, refer to it as a hydrogen bond. I'd like to show you other examples where you can find hydrogen bonds taking place. Okay, let's look at other functional groups. Yeah. This functional group over here, CO What if I have a H and an N and an H? May I ask what functional group is this?
Amino.
Alright, amino. What functional group is this? Carboxyl. Could hydrogen bonding occur here too? Okay. Where? Between what and what? Okay, between here and here. Or here, is it? Okay, so the first step always is to check. Check for polar covalent bond. Are there? They are. This one is partially positive, partially negative. Here's another partially negative one, partially positive. What about over here? We have partially negative, partially positive, partially positive. Is there this hydrogen bonding? Could it take place? And were you saying between, you're saying oxygen, is it?
Between the oxygen and hydrogen and the hydrogen.
Okay, so like that? Yeah? Okay, so that's one hydrogen bond that could take place. Yeah? So the first, this is the last part of today's lesson. Hydrogen bonding. Hydrogen bonding occurs between polar between polar functional groups. Okay, when you find functional groups that contain polar covalent bonds, hydrogen bonding can take place. Right? So as long as there are two things that have partial charges, this attractive force can happen. Okay? So that's the first kind of interaction I would like to introduce to you. Yes, Hoya?
So hydrogen bonds can occur between things that don't have hydrogen.
So for example, are you saying like between here and here?
Yeah.
Possible. Okay? Yeah? Yeah? Must it be oxygen? Must it be oxygen? Not necessarily. You notice here, right? Nitrogen. If I wanted to, let's look at another hydrogen bond. This nitrogen, technically, right, if I wanted to, can interact with this hydrogen here, right? Negative and positive. Hey, sorry, how young? Actually, your point was correct. In a hydrogen bond, you will tend to find one of the parties is a hydrogen. One of them tends to be a hydrogen. Okay, in that interaction. Yeah, I'll give you some time to take down notes, organize your OneNote. Take down notes. And if you have any questions, please ask me. Biology is a topic where things can snowball very fast. So the faster you clear, then the better things get for you. You just get better and better and better. If someone in your pair is done, could you put the water molecules back in the ziplock and pass to the front? Yes. The number is it? Don't need. Okay, great question. So, the ones you will encounter will always be these two we give you. Don't you memorize per se, you know that oxygen is more than this. Don't you remember the number? Just know that if you see O and H, right, it's going to be polar. Okay? Question? Question? No, we clear now. Any question, we clear now. Say again. Oh, between a hydrogen bond and covalent bond. Okay, great question. Okay. A question has been raised. What's the difference between a covalent bond versus a hydrogen bond? Okay. Number one, a covalent bond involves sharing of electrons between atoms. A hydrogen bond does not involve any sharing of electrons. It is purely like if I have two magnets very close to each other, they feel an attraction to each other. That's all. There is no sharing of electrons. This bond, hydrogen bond, isn't even as permanent as a covalent bond. You saw how the water molecules, if they find another water molecule, can just attract elsewhere already. So think of it as two magnets that are close to each other, they just feel this attraction to each other. That's why, you notice, I didn't use a solid line. If I had drawn a line like that, it would mean that they are sharing electrons. Instead, I use somewhat of a dotted line. This represents that it's temporary, it's not a real sharing of electrons, it's just an attraction to each other. Okay? Thank you. Any more ziplock? Sorry, did I answer your question? Okay. Do you all feel okay so far? I need to know if you're okay before I move on, because one thing links to the other. Okay, so far we've learned about functional groups. We learned that some covalent bonds are polar in nature. Because it's polar, we see that there's an attractive force between polar groups. What about non-polar groups? Do they attract each other? Okay, do non-polar functional groups attract each other? Since they are not partially charged in any way, do non-polar groups attract each other? Okay, that's the next question. Okay, I have 15 minutes left. I have this very fun activity. I'll let you all try. Okay, so you all help me out. Everybody take, each pair take two vials, okay, 2 vials of water. So 2, 4, 6. Okay, each pair take 2 vials. 2, 4, 6. 2, 4, 6. Wow, I really feel like a clown, you know. Every time I come to class, there's so many props. Okay, ready? Okay, next, I'm going to distribute sand. I would like, can you take out the cover of the water? I'm going to put the sand on the cover. Okay, I need your help. Can I get your help? Okay, Alpha will go around. He will give you 2 spoonfuls of this particular sand. This is normal sand. Okay, you will take 2 spoonfuls and put it onto the lid of one of your lids. Okay, you do it fast. Okay, I will go around with this special orange sand that I call hydrophobic sand. That means sand that does not like water. Hydrophobic. Okay? And can you stand by the other lid so I can put 2 spoonfuls of this magic orange sand? Okay, quick, next lid. 1. Yeah, that's all. 2. Sorry, I spill everywhere. Okay, next. It's okay. Later your class rep going to clean up. Okay, 2. Okay. So exciting. Okay, this one is very exciting. 1, 2. Okay, next. 1, 2. Hey, how far? 1 leg only lah.
Okay, I make a.
How far? You have one job.
No, it's okay, doesn't matter.
Okay, so you should have 1 leg of orange sand, 1 leg of white sand.
I only did it for like 1 minute.
Okay. Okay, anyone else haven't got orange sand? Ayo. Like putu mayam like that. You know what putu mayam is? Apa I faster than you? Okay, everyone stand by. So you have 2 sands, right? One is normal, one is orange. This is our next activity. We are going to put the sand into the water. Okay? You can take a video if you want to, or I would like you to just take a photo at the very least. Okay? Yeah, okay, so this is what we'll do next. All you will do is to pour the sand into the 2 vials. Wait, I must see carefully, later you're blur. The normal sand put in 1 vial, orange sand put in another vial. Okay? But before you put it in, you can make a prediction on what you will observe before you pour it in. Okay? Once you have made a prediction, you may pour it in. Okay, make a prediction first. What do you think will happen if you pour normal sand into water? What do you think will happen if you put orange, the hydrophobic sand into water? Once you predicted, please add the sand in and take a photo. Has anyone added the sand yet? Come on, go. Alright. Okay, for those that put the orange sand, I would like you to give a little push on the top. And watch what happens. So yeah, you can push deeper. Okay, give the orange sand a push. What happens when it enters the water? Take a photo then. Okay, you can take a photo then. Whoa. Pretty cool, right? Okay, so this is the power of one note. I would like you to take a photo, include it into your CA. We want to capture these experiences that we have in class. How far do I have to go until 10:30? Okay, once done, I'd like you to close the lid on top of each vial. That's what you'll return to me later on. Hey, what are you doing there? It's a mess. Okay, close the lid on top. That's what you'll return to me later on. And then I need to go through the trouble of separating this. So I'll go back to my subroom, right? Now I'm going to try to separate the sand already for the next class. Yeah, then the next class is 302, and then the next class is in 1 hour's time. So I need to take it back. Yeah, I need to quickly filter in 1 hour's time. Okay. Okay, so I appreciate you participating in activity. Now I'd like you to also participate in the conversation. What do you observe in each vial when you add normal sand and then the hydrophobic sand? Could I hear some responses? Okay, what happens when you add the normal sand into the water? Okay, number one, you saw that the sand kind of sink. Okay, what about the hydrophobic sand when you add it into water? At first it float, right? Why was it floating? Okay, do you know what hydrophobic means? Yeah, phobic means there's a fear of. Hydro means water. So this is scared of water. Let me tell you why is this sand so special. Because on the surface of this sand, we coated it with a lot of carbon and hydrogen bonds. Carbon and hydrogen bond, this covalent bond, is non-polar in nature. Yeah? Whereas the water molecules over here, which is made out of H and O and H, this is polar in nature. So what do we observe? Non-polar and polar functional groups, they don't attract each other. In fact, they want to exclude each other. Right? Okay, did anyone push the orange sand downwards? Yeah. Okay, what do you observe when you push the sand downwards? Okay, it sinks. Other than sinking, does it sink in a different way? It clumps together, right? We noticed that when this sand went into the water, it clumps together. Okay, my question now is, why is it clumping together? Okay, let's listen to Charmaine, everyone. Everyone, let's listen to Charmaine. Charmaine, will you repeat yourself loudly? Make sense? All of this sand covered with non-polar groups, they are afraid of water. So if you submerge them in water, right, the only way to minimize the surface area in contact with water is to come together. Right? So it is as though there is an attractive force inwards. Because the water around it, they don't like the water around it. So they are clumping together. So this is the next kind of interaction I would like to introduce to you. This is called the hydrophobic interaction. It is a kind of interaction that happens only if you submerge a non-polar groups underwater, then they come together. Okay? A hydrophobic interaction is a force that only appears when it's surrounded by water. Because we want to exclude each other, we come together. Imagine a bunch of Singaporeans, I send you overseas to a foreign land, right? Because you're in a foreign land, you want to come together, you feel a security with each other. That link that you have with each other as Singaporeans, that is like a hydrophobic interaction when you're in a foreign country. But if you're in Singapore, actually you all will just spread out, right? Yeah. So hydrophobic interaction only occurs when you take a bunch of hydrophobic things and put it in water. Yes, Haya?
So it's not actually the sand that is hydrophobic, it's just the coating.
Yeah, the coating is, yeah. So, I'd like you to think now, your homework for today is this. Can you predict what will happen if I take hydrophobic sand and rather than put it in water, I put it in oil? This is what oil is made up of. Oil is made up of a lot of carbon and hydrogen. Okay? If I put hydrophobic sand in oil, I would like you to predict as your homework, how do you think this hydrophobic sand will interact with the oil? Okay? If you understood what happened here, this will be doable for you. Okay? So today we did one extra thing. hydrophobic interaction. This is between polar groups. This is between non-polar groups. Okay? Can I get you to submit online, okay, your CA 1.1A, a digital copy in Google Classroom? Is it fair to request for it by this, today's what day? Tuesday? Okay, what would be fair for you? Okay, can I request for it on Friday? By Friday, I see a nice digital copy of CA 1.1A. Done up well. Okay, fair? Okay, so that's all I have for lesson today. I would like to collect back all your files so I can filter in 1 hour. Okay? Could I get your help to help me stop the video? Good. Okay, could you pass the files to the front?
Bye.
Very good, huh?